We performed a CFD simulation of a quadcopter using ANSYS Fluent software. A quadcopter is a type of helicopter or multicopter with 4 rotors. In this project, we intend to obtain the dynamic stability derivatives for our quadcopter. We modeled the geometry using SpaceClaim software. Next, we meshed the model using ANSYS Meshing software. Finally, we completed the numerical simulation using ANSYS Fluent software. First, we import our mesh file in .msh format into the Fluent software. For this, we click on the File menu. Then we click on the Read option. Then we click on the Mesh option. Finally, we find our mesh file and import it into the Fluent software. First, we start with the Setup section. We click on General. In the General section, we click on Scale. Here, the general dimensions of the computational domain are shown along the Cartesian coordinate components. We click on Display. Here, the boundaries and zones inside the computational domain are presented. The computational domain is related to the airspace around a quadcopter. In addition, we have created several distinct and separate zones in the domain's interior. A spherical zone around the quadcopter's body, and 2 disk zones around the front and rear of the quadcopter's blades. For the solver, we select the pressure-based option. We assume that there is an incompressible flow. For the time solver, we select the transient option. Since we want to simulate the moving body within the air, the calculation is time-dependent. We click on Models. We click on the viscous option to specify the turbulent flow regime. We assume there is a turbulent flow in the computational domain, so we choose the K-omega SST model. We click on Material. Here, we specify the materials utilized in the computational domain. Note that we use the default materials, air for the fluid zones and aluminum for the solid zones. So we click on Air. In the properties, we determine the density and viscosity for air. We click on Cell Zone Condition. The computational domain consists of an overall main zone containing 3 separate zones. First, we select the main zone corresponding to the airspace around the quadcopter. We set air as the fluid flowing in this zone. Next, we select the zone around the rear blades of the quadcopter. We intend to utilize a user-defined function, or UDF, to model the quadcopter's motion during flight. According to the UDF, a forced oscillating motion on the quadcopter is modeled to capture the dynamic stability characteristics. First, we need to import and load our UDF into the Fluent software. So let's go to the User-Defined tab. Then, we click on the Functions option. Then we click on Compile. Here we click on Add. We find our UDF file and select it. Here, we set the air pressure gauge through the outlet. Next, we select the symmetry boundaries. As expected, we use the symmetry boundary condition. Finally, we select one of the wall boundaries. As expected, we use the wall boundary condition. We consider this wall as the stationary wall. We similarly set the other wall boundaries. After the Setup section, we go to the Solution section. We click on Methods. In the Pressure-Velocity Coupling section, we select the coupled method. Then, we determine the discretization methods for each equation. Finally, we click on the Calculate option to start the calculation process. After completing the calculation, we go to the Results section. Then we click on Graphics. As you can see, The pressure distribution contour on the quadcopter body is displayed in the graphic panel. The pressure variations at different points are completely noticeable. Since our simulation is an unsteady state, we intend to study the pressure distribution over time, so we click Calculation Activities. Then we click Solution Animation to create an animation. Here, we determine how animation files are created, so we specify that the data file is saved at every time step during calculation. In the Animation Object section, we select the pressure contour that we created a moment ago. We click on Contour again. We want to create a plane to display the contour on it. Therefore, we click on the new surface. Then we click on the plane. We create a plane parallel to the XY plane that passes through the middle of the computational domain. Here, we select the newly created plane to display the contour on it. As you can see, the pressure distribution contour on the quadcopter body and in the airflow around it is displayed in the graphic panel. In addition, we obtain a plot of aerodynamic coefficients over time utilizing the report definitions. Here is a plot of lift coefficient variations over time. Here is a plot of moment coefficient variations about the x-axis over time. Here is a plot of moment coefficient variations about the y-axis over time. Here is a plot of moment coefficient variations about the z-axis over time. Thank you very much for being with us. I hope you are satisfied with our training. The Mr. CFD group will always be ready to provide you with training services.